for the invitation. It's a great meeting, and I'm particularly glad to see meetings which try to bring people working at the intersection of traditional solid-state physics and cold atoms. And so that's how I try to structure my talk today. And while the work was really done by my younger collaborators, so the kind of solid-state part was really done by Manuela de la Torre, who's in Baravan University, and the cold atoms part, which I'm presenting today. Sort of some of the ideas go back to Takuya Kitagawa, and more recent work was done by Fabian Grust, and also Michael Knapp, who just left Harvard to start his group in TU Munich, and also Richard Schmidt, who is still at Harvard. And what made this work particularly interesting is the opportunity to collaborate with instrumental groups. So I'll tell you about recent collaboration with Emmanuel Bloch group, ongoing collaboration with Rudy Grimm's group, in his group, and also Eric Hudson and Jenny Hoffman were kind to let us use the experimental data for our analysis. So this is an outline of my talk. First, I've basically divided into two parts. First, I'll try to explore ideas of interferometric probes. I'll start by talking about STM experiments, and it's okay. In the case of cuprates, I will show you that this kind of new interferometric type of studies will allow us to give an interpretation of the peaks, which are commonly interpreted as CBW in terms of the conventional Friedel oscillations. And then when we talk about cold atoms, we'll show how interferometric probes allow us to study topological states. And then I'll talk about non-equilibrium dynamics, and in traditional solid-state physics, this is really motivated by resonant X-ray scattering in superconductors, and I'll show you how thinking about non-equilibrium aspect of this experiment helps to understand some of the paradoxes. And I will also show very close connection of this problem to ongoing experiments with impurity, quantum impurities inside Fermi gases in cold atoms. Okay, so let me start by talking about STM and cuprates, and as I said, the real credit for this work should really go to Manuela de la Torre. Well, I probably don't have to introduce in this audience the idea of STM, so we have some interesting electron system, then there is an STM tip, and by looking at current voltage characteristics, so the differential conductance is the measure of the local density of states. And we're typically interested in some kind of scattering process when, let's say, there was an electron which started with momentum k and then scatters to a state that differs by momentum q. And that's why real space images are typically transformed into Fourier images just by doing Fourier transform of the local density of states. So this is, let's say, what kind of a typical real space image would look like. So this is now the Fourier transform, and one of the simplest interpretation of these images was given by Wang and Li. And the idea is that, let's say you are measuring STM at a certain energy, then what you do, you start with quasi-particles inside a superconductor at this energy, and you can show that sort of lines of constant quasi-particle energy correspond to these bananas. And then you can connect tips of this banana, because tips is where the largest density of states is, and by wave vectors, and this is a set of wave vectors which are most prominent in the scattering. And so you see this peak, this is sort of the usual model of quasi-particle scattering. So one thing which, however, is routinely done with these measurements is that they don't really show us the actual Fourier transforms. They show us the absolute value squared. It is assumed that phases of these Fourier transforms are random, and therefore, in order to avoid this kind of completely kind of scrambling of the phase, they want to get rid of this by taking the absolute value squared. So I'll explain in a few minutes where these random phases are coming from, and we'll also see how we can overcome this challenge. But one thing that I want to point out is that in the last 2 years we have seen a lot of measurements with subatomic resolution. Once you have subatomic resolution, you can actually start measurements and measure not only in the first Brillouin zone, but also in higher Brillouin zones. And one of the things that got us puzzled is that the signal in the first Brillouin zone is different from the signal in the higher Brillouin zones, right? You see this kind of distinct peaks. So, recently this was interpreted in terms of exotic D-wave CDW, but I will discuss that it actually has a different, much simpler interpretation in terms of linear functions. Okay, so let me talk about the origin of random phases in Fourier transform. Imagine that you have an impurity at the origin. Then think of an electron that comes in with wave vector k, and then it gets scattered, it goes to a different plane wave state, there is a certain amplitude, while and possibly different scattering phase. Now just move this impurity to a different position and consider the same scattering process. Then what you can easily work out is that what changes is that there will be an extra phase that is proportional, or that depends on where the impurity is. And now if you are looking at sufficiently large field of view with similar impurities, then you find that this Fourier transform has basically still this kind of scattering amplitude on these identical impurities, but it also has a phase factor which depends on positions of random impurities. And that, of course, can now fluctuate very strongly as we go from one Q to another. And that's why our experimental colleagues try to take the absolute value squared in order to get rid of this. But we'll do something else. So basically think about it this way. So we start with a Fourier transform, and then we just move it by reciprocal lattice factor. One is a reciprocal lattice factor, and then we multiply. It's really like looking at the correlation function. So you have to specify which reciprocal lattice vector you choose, and then you can still have images at all wave vectors, right? You take a product. Why do we want to do this procedure? Because something interesting happens. Just let's consider this product. Let's look at the scattering which originates from this from one impurity. Okay, so this first Fourier transform, as we said, gives us a factor e to I qxi, and then there is a similar factor, but with now a wave vector which is shifted by reciprocal lattice factor, and then what's left is just, you see this reciprocal lattice factor times the impurity position. And now, if we have many impurities, let's say most impurities of the same type, which means that they occupy the same position in a unit cell, this factor is going to be the same for all impurities, and therefore it will effectively drop out. And in fact, so you take the actual Fourier transform of STM, you shift by a reciprocal lattice factor in the x direction, and you see this kind of some interesting patterns that arises, right? And again, so this is color coding. Man, you may wonder, wow, generically it's a complex amplitude, right? So what happened? Well, actually, you can see that now all you have to do is just choose your origin in such a way that this factor becomes real, and then for all wave vectors, basically your signal becomes real, and now you can just talk about positive and negative signals. So it's kind of almost a magic. You just choose the origin of your Fourier transform, and then for all wave vectors, this product of correlation function between the Fourier transforms becomes real, and we find that there is some kind of hidden phase-dependent information which was actually hiding in these local STM images, which has not been realized before. Okay, so let's try to make some sense out of it. So let's just think about moving by a reciprocal lattice factor in the x direction. So that's a pattern that we see in experiments, and actually a simple way of interpreting is to say, well, actually, remember we had this blob in the first Brillouin zone, and then some kind of four-peak structure in the neighboring Brillouin zone. So to get this product, we actually, well, it's going to be basically this signal in the first Brillouin zone had to have the same sign, and here it had to have the opposite sign. And again, when we just look at the original images, because they always showed us the square, we could not see the sign. In fact, you know, and the idea was that all the phase is completely random, but in fact it's not random. You see the random positional impurities were hiding this kind of phase correlations in the signal. Okay, now let's take these H maps. Okay, we call them H maps, holographic maps for obvious reasons, like holography in optics, right? It preserves phase information, not just intensity information. Again, so that's a real signal hiding in the data. And the way to interpret this is that now we have this sort of signals which were in the kind of first, not the original Boolean zone, but shifted by one reciprocal lattice vector either x or in y direction. And we see that they actually had to differ by a minus. So this minus sign actually was realized before by Seamus Davis and collaborators, and indeed that's what we see in here. But of course, what they didn't realize that there is actually also coherence, not just between this certain sign between these signals, but also between signal in this kind of central Boolean zone and the one which is shifted. So basically what this tells us is that if we did not have this random position of impurities, the kind of the Fourier transform of scattering from a single impurity would have this pattern, right? And I want to contrast this again, so this competing d-wave charge density wave. So was always a pattern like this. Because of d-wave they that there is no signal in the central Boolean zone, but rather one only has signals in the Boolean zones which are shifted by one reciprocal lattice vectors. And you can see, so they said that, oh, the symmetry is d-wave. And again, what they verified that, let's say if they shift, basically if they add signals like from this Boolean zone and that Boolean zone, they get 0, or if they subtract them, they add up. And that's also the way we can see the same phase relation, that these two signals come with a minus sign, but in fact they have a well-defined relative phase with a signal in the central Boolean zone. Again, in this scenario, there should be no signal in the central Boolean zone, but clearly, if there was no signal by taking a product, we would not get a sharp peak. And also notice that the overall symmetry is fundamentally S-wave, although this kind of local signal is of, locally it looks like a D-wave, but if we talk about overall symmetry, it's still S-wave. So now, well, okay, so far this was really just showing you analysis on the data, right? So how do we think about this? It's really a very simple interpretation of the scattering process. Electron comes in, then we're looking at first order scattering from wave vector k to wave vector k plus q. But when we think about such scattering, we typically write some kind of lattice models. We parameterize everything in terms of quasi-momentum. So how do we get information about the actual wave vectors, right? Because we go outside of the Boolean zone. And the answer is, well, we actually have to use one-year function. So the original idea, let's say, was already in Danny Podolsky's PhD thesis, but one really has to do it more carefully. Again, the bottom line is that basically when we think about, let's say, Fourier transform of wave vector q, right, we just have to transform, take this relation, move the wave vectors k and k plus q into the first Boolean zone, but then keep one-year function at the original wave vectors. And you can say, oh, one-year functions are not well defined, but here we actually have definition is really given in terms of the block functions, which are well defined. So we have a block function, then we know that it's periodic with a period of 1 unit cell. Therefore, its Fourier decomposition is given in terms of reciprocal lattice vector. So this definition of one-year function is just the appropriate Fourier component of the block function. So, and really, again, going back to what we're trying to describe, so you see that if you look at STM images, right, you see these peaks which don't seem to change with energy. So what this shows you is basically different colors, right? These dots, they correspond to different voltages, and this Q is different Y vectors, and you see peaks, right, which do not depend on the voltage. This is the experiment in this color coding. And it was argued that, oh, because they're not moving, they're non-dispersing, this is really CW. But in fact, you can do this very simple calculation that I showed you, and it actually gives you precisely the same non-dispersing features. What was crucial in this calculation, what was different from early analysis, is that Emanuela put in a finite lifetime. Because people are used to the idea, oh, if you are talking about Friedel oscillation, you actually see dispersion. As you change the voltage, your wave vector is changing. But that's only if you assume kind of Jose particles is very long lifetime. As soon as you have a finite lifetime, you can actually very naturally get all of the STM signatures, all these non-dispersing bits. And this is also true about resonant X-ray scattering, but okay, I'll not focus on this, and this is not the main thing. But to cut the long story short, we saw this pattern in this Fourier spectra. So how do I understand this? Well, it turns out that all you need is very natural, very simple one-year function. You can roughly think of this ring process, kind of copper sides, And then we're looking basically at orbitals which are centered around oxygen, so it's sort of like Rice and Young type of wave function. In fact, also people doing first principle calculations also predicted this for the Fourier function, which should be seen in STM, except the width of the wave function they predicted is quite different from what seems to give a good job, the best job in describing experimental results. So that, again, is basically, if you take this simple x squared minus y squared wave function, this is what you predict for the for this kind of this G map, something basically this kind of Fourier transform, if it was not obscured by random positions of impurities, and that's what you predict for the H maps. And again, so this is this theoretical prediction, and this is experiment, and I hope this looks very convincing to me that we get all the same phase relations that are present in experiments. Okay, so in some sense, I think about it not so much as, you know, like a way of, I think it's useful as a kind of more practical interpretation of what's happening in cuprates, but at least in cuprates, I don't think there was much debate about the nature of electronic wave functions. It's just convenient material where we know that it's a one-band model, but I think now we have subatomic studies of much more exotic materials, say materials based on heavy fermion superconductors, where there are still debates about which bands contribute to superconductivity. We have studies of topological materials with linear functions that sort of mixed with spin, and I think there, these H maps would be very interesting to generalize to spin-dependent STM. So I think this is a very powerful tool for really figuring out what kind of the nature of electronic states which are being probed. So it's a very useful new way of analyzing STM experiments. But the recipe should still be the same. You measure your local density of states, you do Fourier transform, then you do this holographic images, which is basically just shift by reciprocal lattice vectors multiplied. And on the other hand, if you want to make a theoretical model, you start with some lattice model, you start with the linear function, model of scattering, and then compare with your predictions for the holographic maps. Okay, so this was an example of why interferometric studies are very useful for electron systems. Now let's see how they can help us to study ultra-cold atoms. And the question that we want to address is really, well, at least something that I found quite interesting is, when we talk about traditional magnetism, we talk about order parameter. But then when we talk about quantum Hall systems, so states with topological order, well, is there something which is like an analog of the order parameter? And the answer is yes, and this is usually known as kind of very exact case. So let me explain it to you in the simple one-dimensional case. So again, we have one-dimensional potential. We, as we know, solution of Schrödinger wave function given coming in terms of the block waves, and then there is a block wave function. And we should always remember that actually when we talk about the Brillouin zone, the opposite ends of the Brillouin zone should be identified. Even though we're used to 1D Brillouin zone as being a segment, it's really a circle. And therefore, when we define a vector potential, right, so it's a usual vector potential, it just shows you that the block functions, different wave vectors are not orthogonal to each other. Now, and it's a vector potential because we can do gauge transformations, right, to redefine a phase. But if we calculate integrals over closed contours, such as, you know, over the Brillouin zone, it's this quantity which is invariant with respect to kind of a small gauge transformation. Of course, well, let's say it's just invariant and the gauge transformation. So that this very exact phase is really kind of the analog of the order parameter for topological states. And let me give you one example where this is important. I will already give it in the context which is relevant to cold atoms. So consider a model where you have a one-dimensional chain, but your tunneling alternates weak, strong, weak, strong, weak, strong. So in solid-state physics, this comes from polyacetylene. It's actually a good model for describing polyacetylene. In cold atoms, this is realized using bichromatic lattice. Look at this. So you have this kind of longer wavelength red lattice and shorter wavelength blue one. So if you add them up, you have low barrier, high barrier, low barrier. So if you think about tunneling, strong tunneling, weak tunneling, and so on. And now let's try to describe a Hamiltonian for such system, well, we have two sides per unit cell, so it has to be a 2x2 matrix, and we need to diagonalize it in, we know that it can be diagonalized in momentum space, so for each k, our Hamiltonian should be a 2x2 matrix, and then we realize that all the terms in our Hamiltonian, they just connect, A and B sublattices. We don't have really terms which are on a single sublattice, which means that in terms of Pauli matrices, we should only have x and y components. So really, the Hamiltonian can be represented as a vector in the xy plane. And we should also recall that, okay, in this vector, right, so it's like basically it's like a two-level system, right, for each value of k. The value of this vector cannot vanish, because if it vanishes, then we really change the band structure by closing the gap. Right? We have two bands, and if at some point this vector in the plane goes to 0, that means that the two bands are touching each other. So if we want to keep a finite gap between the bands, the vector has to be finite. And therefore, if you think about all possible kind of types of the Hamiltonian, of the vector trajectories as we go through the Brillouin zone, it's either one which does not go around 0 or another one which goes around 0, and they cannot be smoothly connected, right? Because trying to connect them smoothly would require us to cross 0, which, as we said, means closing of the gap. And one can calculate these Berezat phases and very easily establish that, yes, actually that's what distinguishes these two different types of band structure. In one case it's 0. That's not surprising, because here you can say the entire Hamiltonian can be contracted to a point. It's like a trivial Hamiltonian. Whereas here, the Berry phase is pi, which again is clear because it simply means that it's the usual -1 which spin-a-half particle gets if it makes a 2 pi rotation. Okay, so how can we measure it with with tools of atomic physics? So let me remind you about one of the basic tools which you studied in your introductory quantum mechanics. It's called Ramsey interference. Take any two-level system, right? Let me call these two states as up and down states. This can be ground and excited state of an atom to hyperfine state. Well, actually, pretty much anything. And then after the first pi half pulse, we let the system evolve, and generically the spin down and spin up part of the wave functions evolve differently, which we can also think about, in the analogy of spin a half, we prepare the state in the equatorial plane, and now it precesses in the external magnetic field. And then we can do another pi half pulse, which converts this in-plane phase into magnetization, which can be measured. So this Ramsey technique is really one of the working forces of atomic physics. It's the foundation of clocks, all kinds of sensors of gravity, acceleration, and magnetic field. We'll see that it's also useful for probing kind of solid state-like phenomena. So that's how the experiment looks like. So we have, again, this bichromatic lattice, two bands. We start by preparing atoms at the bottom of the band. We do a pi half rotation, which gives us a superposition of spin up and spin down states. Then we apply a gradient of magnetic field, which is pushing atoms in the opposite direction in momentum space. If we wait for basically, okay, you can recognize this so-called block oscillation, right? Which I'm sure you remember. It's basically motion of atoms in momentum space. When they reach the edge of the Brillouin zone, these two spin up and spin down parts of the weight of components, right, of the atoms are actually in the same state. So now we can close the interferometric sequence and measure the relative phase acquired during this evolution, because this is now the same state for the two atoms. And if you look at the phase which was acquired, it has three contributions. One is a geometrical phase, which is precisely what we want to do. Then there is dynamical phase. And in the case of this dynamical phase, well, actually, in this case, it vanishes because you know that points which, because spin up and spin down particles move in a band structure which is perfectly symmetric, so dynamical phase for the two components will always be the same. And then there is Zeeman phase, which has to do with magnetic field and having different, magnetic moments. So if somehow you can make sure that Zeeman phase is not an issue, if you want to measure the Zach phase, you expect to find this interesting phase of pi. Well, it turns out that in a real experiment, this was a bit of an issue, because from shot to shot, magnetic field fluctuates. The way my colleagues explained to me, a subway, runs close to the lab, when a train passes, magnetic field changes. But then there are standard tools from NMR to overcome such difficulties which were implemented. So we're happy to tell you more details. The bottom line is that they were able to do the measurement and they found precisely the space of pi. So this is the first real direct measurement of topological order parameter. So it's not like a consequence of order parameter, not like Hall conductance in the quantum Hall effect, but really the kind of order parameter, which is a very exact case. And then the same idea can be extended to, say, 2 dimensions. Let me give you just example of graphene. In the case of graphene, we know that the band structure has Dirac points. And what's special about Dirac points is that if we integrate this very exact phase around one of these Dirac points, we should get pi. It's very important pi because this explains why, for example, the quantum Hall plateaus, integer quantum Hall plateaus for graphene are shifted by 1/2. It's really due to this very phase of the Dirac point. And so now we can make a trivial modification of this argument. Now the 2 trajectories should simply go in different sides around this Dirac point, and that should give us a phase of pi. And that's precisely what was measured in experiments at LMU. And then one can actually look at even multi-band generalizations, right? Imagine, like, if we think about graphene, so now you can think about this very phase as being not just a phase, but really a matrix if you think about 2 bands. And of course, what one worries about, well, now there is dynamical phases, but if a particle moves faster and faster, at some point, this dynamical phase no longer matters. So it's as if the bands become very flat. So effectively, in this case, dynamics, the phase relevant for dynamics is all reduced to just geometrical phases. And this, again, turned out to be something that could be probed in experiments. So you can see, let's say, so this was the trajectories when they go from a point in the center of the Brillouin zone to different final points, so small velocities. Basically, the measurement really correspond to adiabatic motion, but then as they move faster and faster, there is some kind of a saturated limit, which is really the regime where the only thing that matters is this kind of matrix type very phases. Again, I'll be happy to give you more details about this. I'll just point out that one thing that they did measure is that if you go from the center of the Brillouin zone to another center of the Brillouin zone, so it turns out one can make a general argument that this should really just measure the centers of linear orbitals, right? And we know where linear orbitals are for the graphene, it's A and B. And so you know that, let's say, the difference of the centers of linear orbitals times reciprocal lattice vectors will be pi/3, and that's precisely what was measured in experiment. So it's really, this kind of interferometric tool is very powerful for really studying topological properties of band structure. But in fact, it's more than that. You can extend this to interacting systems. So let's say we have some kind of fractional quantum Hall effect, like fractional Chern insulator, the Killing factor of 1/m. In this case, well, we know that typically the many-body Chern number that we define has to do with the overlap of the many-body wave function. But that's, again, something you can study as a theorist in the numerics, but it's not something like which you can measure experimentally. The question is, well, how can we find an experimental measurement of this topological environment? So it turns out that the trick you can do is to add one impurity. But it has to be a mobile impurity. So that's the difference between condensed matter and traditional kind of impurities, how we think about them in condensed matter and cold atoms. Here we want an impurity that can move. And when impurity can move, right, let's say it can still move dressed by what's happening, by sort of excitation of the many-body system around it. So in this case, we want an impurity that has repulsive interaction with the surrounding particles, and then it can bind a vortex, right? And if it can bind a vortex, this motion of an impurity actually will carry all the phases that the vortex acquires, right? So basically, you know, there's a famous flux particle duality in the quantum Hall effect. So when a vortex moves, it sees original particles as sources of flux, and so it acquires a phase. And so even if we start with an impurity which moves in, which by itself is not topological, doesn't have any Chern number, but when it binds a quasi-particle, you can sort of do simple counting and show that it will actually move in an effective magnetic field which is generated by the finite density of the surrounding particles, and in fact it will acquire a Chern number which is inverse of its fractional charge, which is 1/m. So, one can do very simple numerical calculation to verify it. So we took fermions at a filling factor of 1/3, flux density of 1/4. We take an impurity with repulsive interaction which bind this vortex. And then we really just look at the winding of this Zach phase. It's a way of measuring the Chern number. And as expected, we get a Chern number of 3, which shows that yes, such topological impurities can be a probe of fractional quantum Hall state. So this idea of basically we're really using an impurity as an ancilla cubic, which acquires the phase, the many-body kind of phase becomes imprinted on the impurity, and then you can measure it as the original, as a single particle. Okay, so now let me move to the second half of my talk. I told you about say interferometric techniques as something common between ultra-cold atoms and condensed matter systems. Now let me talk about non-equilibrium dynamics. So and let me start with something that I'm sure you remember, and that's X-ray scattering. So when people talk about X-ray scattering, what textbooks tell us is that, well, it just measures density-density relation function. Just look at momentum transfer, you look at the energy transfer, and at the response function of the system at this wave vector and this frequency. Well, but actually it turns out that this traditional so-called hard X-ray is not so useful for some of the novel materials, because the interesting physics is happening in the conduction band, whereas this kind of X-ray is sensitive to all the charges. So it's primarily sensitive to core electrons, ions, and so on. So you somehow, people wanted to amplify the role of the conduction band. And that's where they started using resonant X-ray scattering, where the incoming photon energy is tuned so that the electron is promoted from the core orbital precisely into the conduction band. And this really amplifies the kind of cross-section of what's happening in the conduction band by orders of magnitude. But what I will show you is that this actually turns it into a much more challenging probe to understand. It's no longer the usual density-density response function, but it's really a process which requires studying non-equilibrium dynamics. And that's why some of the puzzles which people interpreted actually can be resolved very naturally if you think about it as a non-equilibrium process. Well, I'll give you just one example, something that really got me thinking about this. So this experiment is done in high TC cuprates. So this is a phase diagram, which I'm sure most of you have seen many times. What is important to me is that there is a regime called overdoped regime, which is sort of like Fermi liquid. Like basically all the measurements show that it's not so different from traditional methods. In particular, neutron scattering, which is like a gold standard of probing spin excitation, did not show pronounced magnetic excitation. On the other hand, this resonant X-ray scattering demonstrated some dispersing peaks, which were interpreted as magnets. And let me explain. So this is really what's an example of the data. So this is experimental data as a function of energy transfer for different momentum transfer. So there is always a peak at zero wave vectors, at zero energy transfer. This is elastic peak. Everything gives you elastic peak. My colleagues told me when sample called it to be elastic peak. So that's something one has to subtract. So therefore, that's what they did for us. So this blue feature is really this, is what's left. And you can see that now for different momenta, you see this kind of this blue response, which looks like a peak, which seems to change its position, which looks like a dispersing mode. And so they said, well, it's a collective mode, right? It has a dispersion. And of course, whether you still have well-defined collective modes or not is very important, because that matters when we're discussing the mechanism of superconductivity. Okay, so, and I'll show you, and then there are other puzzling facts which I'll tell you about later on. But the goal of this talk is really to show you that some of these kind of problems go away when we give up on the traditional interpretation of X-ray scattering as, density response function, but think about this non-equilibrium problem. Okay, but what I will do now is, I have to sort of make you believe that when I talk about non-equilibrium dynamics, it's something that I can actually calculate, right? So I'll do it in the following way. I'll tell you about the problem in which we really know the underlying microscopic model, in which we do not have any doubts about the underlying Hamiltonian. We'll describe dynamics and we'll compare to experiments, and we'll see that we actually do a pretty good job, and after you, hopefully you believe me, then we'll go back to this resonant X-ray and try to interpret the data. Okay, so now the experiment that I'm thinking about is the following. In cold atoms we have Fermi gas, and then we have an impurity atom. And think about this impurity as being either very strongly confined or being very heavy. And this impurity particle can be in two internal states. So in one state it does not interact with the fermions. In another state it scatters them very strongly. And now what we do, we actually do the same sequence that we discussed before, Ramsey sequence. We prepare an impurity in the spin down with the Fermi surface. And then we do a pi-half rotation, which gives us a superposition of impurity in spin down and impurity in spin up. And then we let it evolve. So the part of the wave function that has spin down impurity doesn't do anything. It's pretty boring, right? Nothing changed from the point of view of fermions. But the part of the wave function that has impurity with spin up is another matter. Right now, actually, fermions suddenly see a local potential, which does a lot of scattering. So this state, this kind of evolution of the Fermi surface, has a lot of scattering, there's a lot of particle holes generated. So we're really sort of growing a giant cat where here there are no particle hole excitations, and here, as time progresses, we generate more and more particle hole excitations. And now when we do a pi-half rotation, we're basically measuring the overlap of this fermionic part of the wave function. In other words, we're really measuring this time-dependent overlap. It's like a quench process, right? Sometimes in technical language, this quantity is called the Loschmidt effect. You start with the Fermi C, which is an eigenstate of this H0, but then you evolve it with a different Hamiltonian. In this case, this different Hamiltonian is actually Hamiltonian that has local scattering. Okay, so that's a strange object. So why would you want to measure this? So let me take a step back. So for younger people, to explain that this is all tightly connected to kind of observation that even small perturbations in Fermi systems have dramatic non-perturbative effect. That's known as Anderson orthogonality catastrophe. So let me start by considering a kind of equilibrium problem. So imagine that again we have unperturbed Fermi C, and then we have a Fermi C which was very weakly perturbed by just a single impurity. And then you take an overlap of two of these ground states without the impurity and with the impurity. Even though this impurity can be very weak, in the thermodynamic limit, this overlap goes to zero. So that was first pointed out by Anderson, and in a nutshell, the argument is as follows. Well, think of each single particle wave function, which changes very little. Let's say the overlap of wave function is 0.99. But then you have to take it to a huge number, which is the number of atoms in your system, like Avogadro numbers. And of course, any number less than 1, which when you take it to this huge macroscopic number, will give you 0. It's really a fundamental property of the Fermi gas, which underlies many phenomena in condensed matter, from, let's say, Kondo effect to, let's say, tunneling into nitrogen liquid, and so on. And in fact, one can do some calculation and show that this overlap goes as a power law in the system size, where the exponent is controlled by the phase shift of fermions at the Fermi energy. Okay, but one question you can ask, well, okay, we want to talk about dynamics, so why do we talk about overlaps of the ground state? Well, in fact, remember this kind of time-dependent overlap that we discussed. It actually bears a very close resemblance. If we take a Fermi surface, now we switch on evolution, we switch on impurity, look at the evolution with the scattering potential, this overlap decays in time with the same exponent. And we can very easily understand it. So you introduced an impurity. This impurity generated particle hole excitations, which are spreading out with the Fermi velocity. So if, after the time t, basically the system establishes a new ground state at a length scale, which is given by V Fermi times the kind of how long you waited. So now the overlap is like the overlap of the ground states. And that's where we get the same power law. And actually, this observation goes back to the 60s, when people started thinking about X-ray absorption, and they realized that if you look at absorption from the pore level to the conduction band, it's nothing but the Fourier transform of this time overlap, right? And if you get power law in time, you actually get power laws in frequency. And now you can ask, okay, well, if this was studied back in the 60s, why study it with ultra-cold atoms? Well, in a nutshell, the argument is that cold atoms are a much better controlled system. You know, remember when I told you, well, that what is the answer that we try to give for electron systems is entirely in terms of the phase shift of the Fermi energy. It's not something you can really calculate. Well, unless you ask Steven, he probably can calculate it, but we mortals cannot. So typically, it's some number which, where you have to get it, you have to get, you have to take into account screening and so on. By contrast, in ultra-cold atoms, if you give me the scattering length, I can give you the scattering amplitude at all energies, right? So therefore, it's not only dynamics at long times, which is universal. Dynamics at all times, at absorption at all frequencies is really a universal function. And actually, as a result, when we looked at this, we found something that has not been appreciated before. So if you take kind of this Loschmidt echo, and if you look at the evolution, this kind of Loschmidt echo at long times, yes, you do find power law. But in addition, you find oscillations. And the frequency of these oscillations is precisely E-from. And it's very easy to understand where it comes from. It really can be explained by realizing that kind of these impurity problems, they're one-dimensional physics in disguise. It's strange at first sight, right? We're talking about scattering by an impurity in a three-dimensional system. But if we think about a local impurity, then local impurity only scatters electrons that have angular momentum 0. So therefore, all electrons that get scattered, they have angular momentum 0 and can be classified by the radial quantum number. And so it really sort of looks like some kind of incoming and some outgoing impurities, so it is effectively a one-dimensional system. And what's special about one-dimensional system, that at the bottom of the band you have a singularity in the density of states. You have 1 over square root. And this singularity means that it's not only excitations near the Fermi energy, which gives you this power law, but you can also generate a low-line excitation from the bottom of the Fermi sea, because it has a singular density of states that contributes to this dynamics, and this gives you rise to this oscillation. It's not a super deep observation, this new type of bottom of the band physics. However, people were not interested in this in the context of electron systems just because they didn't want to talk about any dynamics on the time scale of Fermi energy. It was assumed so non-universal and completely out of reach in experiment. But actually now people are beginning to push in this direction with quantum probe experiments. So it is actually maybe relevant even for condensed matter systems. Of course, what you have in the real world is that there is temperature, right, which, let's say, can kill some of this power law decay, and instead it becomes an exponential decay, but let's say it's actually much more gentle on this oscillation. Okay, so to make a long, again, I will not give you details about real experimental systems, but just point out that this is an experiment done by Rudy Grimes. So this kind of cloud is potassium atoms inside lithium from a gas. So this is this kind of purple cloud. So there's actually a small concentration of Fermi impurities inside, impurities inside the Fermi gas, and then they can do precisely the type of manipulations that we discussed, kind of pi half pulses, pi pulses, and they measure decay around the fringes. Okay, let me, I think I'll draw again some subtleties in how experiments were done, because for theorists it's very easy to say, oh, you do very fast pi half pulse, very fast pi pulse. In reality, it's not easy, but they came up with very kind of ingenious tricks to overcome challenges. Okay, but I'll skip this. As a theorist, I'll actually spend this time by telling you how we can do calculations. So the idea of we can actually analyze problems like this, say dynamical problems, but for non-interacting fermions, is very simple. It's basically an idea that if you look at non-equilibrium dynamics of slated determinants, they always stay slated determinants. Because your original wave function is so completely anti-symmetric with respect to any pair of particles. So even as they evolve, this anti-symmetry should preserve. So when you look at evolution of slated determinants, you really have to just keep track of evolution of single particle states and then reassemble a slated determinant. And then there is a very powerful technique that was invented by people in mesoscopic physics, primarily by Levitov and company, which has the name of functional determinant formalism. So this is how it works in a nutshell. So imagine that we have something like exponential operators. This x can be, let's say, evolution operators with some dependent potential. It may also involve, let's say, like some kind of thermal averaging, just Gibbs sum. Let's start with just one operator. We have to take a trace. But we have to take a trace in the many-body Hilbert space, right? We have to average over all occupation numbers. So the easiest way to do this averaging is to go to a basis where this operator x is diagonal. Then you know that the states are either occupied or empty, and then summation over this empty and occupied is very easy. You just basically get a product of these factors when the state is empty and when it's occupied. And then you realize that this can be written as a determinant, but now it's a determinant computed in a space of basically single particle Hamiltonian. So we started by taking a trace in many-body space, and we get an expression which is a determinant in single particle space. So that's what really makes this calculation very easy. And then you can actually extend this if you have more complicated, let's say, a product of two exponentials of quadratic operators. It can still be written as exponential or quadratic operator. So you know that this trick will still work. So you can still write it as a determinant of this combination, but written in single particle space. So it's a very useful tool which can convert, something that needs to be calculated in many-body space. Now you just need to calculate it in single particle space. And you can actually add all kind of, let's say now you have to create annihilate operators which we will need for x. You can still write explicit expressions. Okay, but going back to cold atoms, so again, this was experiment, potassium impurities from non-interacting to interacting. So this is decay of Ramsey fringes, so the dots are experiments for different interaction strength. And so the red line is this functional determinant theory. Again, in principle, as I said, our analysis only works for infinitely heavy impurities. For potassium impurities are only a factor of 7 heavier than surrounding Fermi gas, but it actually works quite well, and okay, I can explain, but I think it's finite temperature. It turns out that in this experiment temperature is sufficiently high, and that's why this works. So for comparison, let's say we can also, this dashed line is a calculation when we if we did not include, if we considered zero temperature response, so then dynamics, let's say the decay would be slower, this would be the beginning of the power law, so this is actually the beginning of exponential decay. Now this blue line is what's known as Chevy ansatz, again for specialists in cold atoms calculation. This is an ansatz when you allow it only in single particle Hall excitation. You see that it does pretty badly, which shows that it's really dynamics which involves many particle Hall generated. It's really many-body dynamics which is being probed. And so we see that, again, we emphasize there are no fitting parameters. In fact, Rudy insisted that we send them our theoretical results before they send us the data. He said that he had bad experience with theorists, kind of working until they get the desired result. So in this case, they just send us a magnetic field, we send them the plot. Okay, and then as I said, the Fourier transform of this is something that corresponds to absorption, to spectroscopy, the usual spectroscopy in frequency space. And so, of course, it's very easy. So this now shows you the dots again, kind of the RF measurements, and the red lines is this functional determinant, again converted to frequency absorption. And you can see quite decent agreement. So, okay, I think with this we sort of just built our confidence that we understand what we're doing. And again, sort of from the point of view of like the breakthroughs, what I'm kind of excited about is that we can see this beginning of the oscillation. And though we cannot see power law, we see this kind of dynamics on the scale of E Fermi, right? We see the birth of the polaron. I'm not aware of any pump and probe experiments in condensed matter that can really resolve something in the scale of Fermi. On Fermi timescale. Whereas in cold atoms, just because they have such low energy, the timescales are much longer, it turns out to be easier to observe in experiments. Okay, really out of time. So now with this kind of confidence, let's go back to this resonant X-ray sketching. So when we talk about, let's reconsider resonant X-ray sketching. So we have, the way it works is that the photon comes in, right? Photoexcites electron into the conduction band. Then this core orbital state has to be refilled, and photon flies out. So we leave behind a particle Hall excitation. So if one looks at the amplitude, this is the so-called Kramer-Steisenberg relation, which one has to calculate. What is tricky about this is, that this. Remember, we said the role of the core Hall potential. So that's what shows up here. This Hamiltonian, which, with respect to which we have to evaluate. The dynamics, it involves the potential of the core Hall. So how do we calculate? Well, the way we do it, we convert it from frequency space to time evolution. So that's rigorous transformation, including the finite lifetime of the core orbital. But now it looks like a very nasty quench problem. So you see, we add an electron into, it's like a history of the system. We add an electron on side M, then we evolve with a Hamiltonian, which has extra four-hole potential on this side. Then we annihilate an electron. And then this is like Bra and Ket. We do analogous thing, but on a different side. So this is Ket, this is Bra, right? We add an electron on side N, and then evolve with a Hamiltonian that has extra four-hole potential on side N, then we annihilate an electron. And then we take an overlap of the two wave functions after some evolution with the original state. So it's pretty nasty again. So people like say, even though we're now doing this for non-interacting electron, that's pretty hard to do. So let's actually, so we can do it for single band mode of cuprates, but let's say frankly when we try to do it for pnictides, okay, with many bands, three-dimensional, we couldn't do it, but probably people who are better, stronger numerics would be able to handle this. So this is again what we're trying to explain. So this is this Riggs state. I remember this dispersing feature, so in the overdoped regime. Now what we do, we just do that non-equilibrium calculation. So this green line is experiments, and this black line is actually what we compute. We take a standard band structure of cuprates again. We don't fit the band structure. We just take what's known. The only parameters that we take is the core hole potential. Again, as my colleagues told me, it's really not known where it's coming from. And, but it's kind of a reasonable number of sodium electron volt, and in fact we very naturally get precisely the same dispersion as in everything experiments. So this model of essentially non-interacting electrons in fact works very well for describing the peak. Okay, so this high, you may worry about this high energy, so it turns out that in real experiments at high energies you start getting transition into a higher band. So this is physics beyond a single band, which is obviously not included in our calculations. So let me now give you a bit more facts. So another reason why people said that, oh, this signal cannot be due to non-interacting electrons is the difference between spin flip and non-spin flip channels. If you remember your kind of basic solid-state physics argument is, oh, if we have non-interacting electrons, then response without spin flip and with spin flip is just the same Linhart function. They have to be the same. But in this case, when they measured this Riggs, they actually saw that with a spin flip and non-spin flip, you see they look quite differently. With non-spin flip, it's pushed to higher energy, whereas non-spin flip is at lower energy. They said, oh, but some interactions must be involved which sort of soften the spin flip. So we're talking about magnets. But actually, so the dots experiments, these lines, again, the same model, we simply do this